Hello, welcome all. Myself, Dr. Girish Hampanava, Assistant Professor, KLA College of Pharmacy, Vidyanagar, Hubli. So, in this third episode of Fluorimetry, we will be discussing about the fluorescence quenching process. So, just briefly to tell about the fluorescence quenching phenomena. This fluorescence quenching or quenching is a physical-chemical process which decreases the fluorescence intensity of the light emitting molecules. Just to simplify, this quenching is a process where the fluorescence intensity of the emitted radiations or the emitted radiations from the molecules, if the intensity is going down by the presence of some other molecule or by some other process, if the fluorescence intensity is dropping, we call it as the quenching phenomena. A variety of molecular associations can result in quenching, and they include excited state reactions and molecular rearrangements, energy transfer, ground state complex formation, and collisional quenching. So these are the variety of phenomena in which may result into the quenching process. Just to briefly say about this excited state reactions, this means when a fluorescence is happening with a molecule, if that fluorescent excited molecule, if it is showing fluorescence while emitting the radiations, in that excited state, if there is any reaction that is undergoing, that molecule is undergoing, in that particular case, it loses that excitation energy to that particular reaction, and hence there is no emission of fluorescence that is happening. So that is one reason, or that is one way in which the fluorescence intensity is lost. And also in some molecular rearrangements, the fluorescence intensity is lost, wherein which a molecule rearranges itself so that a fluorescent molecule will turn to a non-fluorescent molecule. And there may also be a sort of energy transfer that may happen in case where it loses the energy or it dissipates the energy as a non-radiative process, wherein which the molecule will return to the ground state from the excited state without losing any fluorescence energy. Ground state complex formation is a complexation process of the molecule in the ground state itself, so that the molecule won't excite and it won't reach the excited state at all. The other one is a sort of collisional quenching, which we'll be discussing in detail in today's discussion. Collisional quenching is a phenomena where a molecule loses its excess energy to a neighboring molecule just because of collision, and this collision, a very sufficient or a very enough energy is lost in this collision process, and thus a fluorescent molecule will not show any fluorescence because of this collisional quenching. So there may be other factors as well which may contribute for this quenching phenomena, like change in the pH, change in the concentration, change in temperature, viscosity, or presence of some other materials like oxygen, heavy metals, and some specific chemical substances. If they are present, they may also possibly quench the fluorescence. So we have something called as quenchers, and this quencher will reduce the fluorescence intensity of the sample of interest so that there is drop in the fluorescence intensity of from the sample. So reduction of fluorescence intensity of the sample in the presence of substance other than fluorescent analyte. Other than analyte, if there is any other substance which is contributing for the reduction in the fluorescence intensity, we call them as quenchers. I have some classic examples of quenching agents, wherein which they may be thiocyanates, chlorides, iodides, disulfides, or nitric oxide. So the typical fluorophores or fluorochromes or fluorophores, what we call, which will be quenched by these following quenching agents. For example, anthracene, the fluorescence intensity can be reduced by using thiocyanate as a quenching agent. Similarly, quinine, we can use chloride as a quenching agent. If it is tryptophan as a fluorophore, then we can use iodide, which will decrease the fluorescence intensity of the tryptophan. We have tyrosine, where we can use disulfide as a quenching agent. And if it is a naphthalene, which is a fluorophore, or if it is a molecule of interest, we can use nitric oxide as a quenching agent. So coming to the types of quenching, there are 4 different types of quenching. I'll just read out all the 4. The first one is static quenching, also known as contact quenching. The second one is dynamic quenching, also known as collisional quenching. The third one is chemical quenching, and the fourth one is concentration quenching, or also known as self quenching. Coming to the first one, that is static quenching. As I mentioned, it is also known as contact quenching. So static quenching, it occurs at the ground state of fluorescing molecule. It can be simplified by the following mechanism. So just first let me go through the mechanism of this static quenching. F is our fluorophore, or the compound which is showing fluorescence, and Q is nothing but the quenching agent. What happens here in the static quenching is the quenching agent will complex with the fluorophore while in the ground state. So even before the incident radiation is made to fall on this fluorophore, the quencher will form a complex with a very strong bond with the fluorophore, and there is a complex F is to Q, which is a complex, and after this complex formation, when we subject this complex for an incident radiation, here rather than fluorophore taking up the energy, the quencher tends to take up the energy, and the quencher leads to the excited state or goes to the excited state. This star mark, or this superscript with a star mark, represents that this quencher is in an excited stage, and the fluorophore is in the non-radiative form. So the moment the energy which is taken up by this quenching agent, that quenching agent, it comes back to the ground state, relieving the energy that it had taken up for the excitation. So rather than fluorophore being excited, it is the quenching agent which takes up the energy and gets excited. So that is how the static quenching phenomena will quench the fluorescence intensity of the fluorophore, which we are actually interested in. So we have the quencher along with the excess energy being dissipated. So here a complex formation occurs between the fluorescing molecule at the ground state and the quencher molecule through a strong coupling. This static quenching is usually because of the strong coupling that happens in the ground state, and that creates a non-fluorescent complex before excitation of the fluorescence molecule. So this, because of this non-fluorescent complexation which happens, there is no fluorescence intensity by the fluorescing molecule alone. I mean to say, it tends to lose its actual property or its inborn character, and it won't excite itself because it is losing its property because it is forming a non-fluorescent complex. Such complex may not undergo excitation or may be excited to a very little extent, reducing the fluorescence intensity of the molecule. So the fluorophore can form a stable complex with quencher molecule, which I have just now mentioned. If this ground state is non-fluorescent, then we say the fluorophore has been statically quenched. That is what we call this as, there is a static quenching that is happening with this fluorophore. Amount of quenching decreases as the temperature increases, as equilibrium is driven to the unbound state. This is a very important understanding, where the quenching itself is decreased as the temperature is increased. So if I increase the temperature, the quenching decreases. That is because if I increase the temperature, there is no facilitation of this complex formation, and as the equilibrium is shifting to the unbound state, I mean to say, if this is a complex wherein which I am increasing the temperature, then this complex is broken, and this actually is driven backwards to the unbound state, so that the fluorescence by this fluorophore is visible. I mean to say, this fluorophore will take up the energy independently rather being forming a complex. So increase in the temperature actually favors the fluorescence phenomena, rather it inhibits this complex formation. The quenched state is entirely non-emissive. I mean to say, when there is a quenching or when there is a complex formation, this complex as a whole is a non-emissive compound. So there is no emission happening when there is a static I mean to say when there is an complexation which is being formed. There is no fluorescence happening from this complex. Static quenching occurs at the ground state of fluorescing molecule. It can be simplified by the following mechanism. I mean to say this static quenching, or I mean to say this complexation, happens well within the ground state. As you see, there is an image which I have tried to represent here. If you if you put the incident radiation, which is the UV visible radiation in this particular case, the fluorescent molecule has formed a strong complexation or a strong coupling with the quencher molecule well within the ground state. So this molecule or this fluorophore is not behaving independently, rather it behaves as a complex. Once there is a complex well within the ground state itself, then there is no energy being taken up by this fluorophore, because this is losing its inbound character, because it is no more behaving as an individual fluorophore, rather it's behaving as a complex. So the energy what it takes up, the fluorophore, whatever the energy it takes up in the form of electromagnetic radiation, it simply dissipates that energy to the quencher, and thus the quencher gets into the excited state, and that loses the energy into a sort of a non-radiative process in most of the cases, and it is a simple energy which is coming out, and thus this whole complexation process or this whole static quenching will lead to the drop in the fluorescence intensity of this particular fluorophore F. And that was all about the static quenching. And there are some examples for this static quenching. Caffeine and related xanthines and purine will reduce the intensity of riboflavin by static mechanism. If you are studying riboflavin, these are the compounds which acts as the quenchers, that is, it may be caffeine, it may be some xanthine or some purine related compounds. See, this we can take it in the other way around, where when we can estimate these purines or we can estimate the riboflavin just by adding the known amount of quenchers, and if you are able to find out the drop in the intensity, which can be proportionally correlated to the amount of the quenchers if you are trying to find out the concentration of the quenchers, or even if it is the riboflavin in a case, you can even find out the concentration of this riboflavin by using this quenching phenomena. Quenching due to oxygen also follows static quenching mechanism. We will take up this example in the chemical quenching, where the oxygen acts as a quencher and it leads to the drop in the fluorescence intensity. Coming to the next one, that is dynamic quenching, also known as collisional quenching. Collisional quenching always occurs by the interaction of the quencher molecule with the excited molecule of the fluorescing substance, which facilitates a non-radiative energy transfer from the excited fluorescing molecule to the quencher without or less fluorescence. So as the name implies, the dynamic quenching is something what we call as a collisional quenching. Here the quencher molecule interacts with the excited fluorescing molecule, which is our sample under analysis, and because the quencher is colliding with the excited fluorescing substance, the excited substance loses its energy post collision. That energy is lost to the quencher molecule, so that the quenching of the fluorescence intensity happens with the fluorescing substance. A simplified mechanism, I have written it here. This is a fluorescing molecule which takes up the UV visible radiation and it goes to the excited state. I have represented this excited state as a star here. This fluorescing molecule in the excited state, what usually happens is it loses the energy in the form of fluorescence and comes back to the ground state as F. But this usually does not happen in dynamic quenching, wherein which this fluorescing molecule in the excited state, it collides with the quencher. That's why we call it as a collisional quenching. And since there is enough distance between this fluorescing molecule in the excited state and the quencher, this collision happens very smoothly, and because of this collision process, this fluorescing molecule loses its excess energy to the quencher. Thus the quencher enters into the excited state, rather the fluorescing molecule simply comes back to the ground state, and we call that as collisional non-radiative decay, wherein which the F star, which was in the excited state, simply comes back to the ground state because the excess energy is being lost to the quencher molecule. So in order to represent this whole phenomena, I have taken the same image what we had discussed in the previous uh, static quenching. So we have a fluorescing substance where it takes up the incident radiation and it enters the excited state. That's why I represented it as F star. And this excited fluorescing molecule, it collides with the quencher because there is enough distance for interaction, because there is a weak coupling between the fluorescing molecule and the quencher. There is a sort of energy transfer that happens to the quencher, and this quencher in turn enters into the excited state. I mean to say, it takes up the energy and then it may further dissipate that taken up energy in the form of heat, or maybe a radiative process or any non-radiative process. So this was the whole thing where there was a sort of collision happening between the excited fluorescing molecule with the quencher, thus losing the fluorescence property. The collisional quenching also shortens the lifetime of the fluorophore. That's why since the fluorophore it loses its lifetime, or the lifetime of the excited state, because of this collisional quenching. And there are some halides, halide ions like chlorides and iodides, which are known to be a well-known collisional quenchers. For example, quenching, we have an example which we study in our practical as well. Quenching of quinine drug by chloride ions or iodide ions, or quenching of tryptophan by iodide ions, those all follow this collisional quenching process. Coming to the chemical quenching. Chemical quenching is due to various factors like change in pH, as I have mentioned previously. Any chemical factor which is contributing to the quenching phenomena, we account all those factors as chemical quenching processes, like the first being change in pH, presence of oxygen, presence of halides or electron withdrawing groups or any heavy metals, etc. So first, coming to change in pH, I am taking a classic example of aniline, which has some fluorescence between this pH range, that is 5 to 13, and if it is excited at this particular pH, that is 5 to 13, with this wavelength, that is visible radiation at 290 nanometer, it gets excited and it shows fluorescence. But if you change the pH, if you make it below 5 or if you make it above 13, this aniline will lose its fluorescence property. So that is because of the ionization in this particular pH, which is either below 5 or above 13. If there is an ionization that is happening, this aniline loses its property, and thus it loses its fluorescence phenomena. Oxygen is one more chemical factor. Oxygen leads to the oxidation of fluorescent substance to the non-fluorescent substance, thus reducing the quenching process. It is a sort of oxidation that is this oxygen is bringing about in order to bring about this quenching phenomena. Halides and electron withdrawing groups, as I have mentioned, these electron withdrawing groups ideally tend to decrease the fluorescence intensity. That is because they reduce the electronic configuration on a given molecules, and also these halides like chlorides, iodides, and some electron withdrawing groups like NO2, COH, aldehyde, they lead to the quenching phenomena. And some heavy metals in their presence also lead to quenching process, and that is because of the collision, or maybe in some case because of the complex formation. And usually heavy metals they act as a ligands sometimes, and they facilitate the complex formation, wherein which a molecule, a fluorescing molecule, it loses its inherent nature of fluorescence because of the presence of heavy metals, and thus there is a sort of chemical quenching happening in a given system. So the last one is the concentration quenching, also known as self-quenching. It occurs when the concentration of the fluorescing molecule increases in the sample solution. I mean to say, as like we discussed in the Beers-Lambert's law, the Beers-Lambert's law was not obeying beyond certain concentration range. That was because of the excess absorbing species which were possibly leading to that deviations in the Beers-Lambert's law. Somewhat similar, here the concentration, if you increase or if you keep on increasing the concentration of the fluorescing molecule itself, then what happens? The intensity or the fluorescence intensity will tend to drop, and that we call it as the self-quenching or the concentration quenching. The fluorescence intensity here, it is highly reduced in the highly concentrated solutions if the solution is beyond 50 microgram per ml. So as a rule of thumb in fluorescence, what we do is we work with a very dilute samples, unlike in the UV visible spectroscopy where we used to work with a very highly concentrated samples. Here we are not working with the highly concentrated samples, rather we tend to keep our sample concentration in a very less concentrated forms so that they show the fluorescence. So I have tried to represent this particular concentration quenching in this particular diagram here below, where in which the fluorescing molecules, here you can see onto my left, at the low concentration, they are very apart. The fluorescing molecules are very at a very separate, I mean to say they are very far from each other, and when there is an incident light falling on these molecules, they have enough space to take up the energy and to go to the excited state. And once they go to the excited state, they won't stay there for a long time, and rather the fluorescence phenomena, it is a sort of the emission process, which is a radiative emission process wherein which the fluorescence is observed. And similarly, if I increase the concentration here, you can see the molecules are coming very close now in this particular case onto my right. And what happens? The energy taken up by these molecules from the electromagnetic radiation or from the incoming electromagnetic radiation, that energy is dissipated to a neighboring molecule just by a sort of collisional process. But in this case, it is not a quencher, but it is the same molecule which is acting as a quencher with the same neighboring molecule. So what I have represented here is the energy from this excited molecule is dissipated to this neighboring molecule, and that's how this close setup of molecules will tend to contribute for a non-radiative transfer, wherein which there is a drastic reduction in the fluorescence emission, and that we call it as a concentration quenching. So basically avoiding this close packing of the molecule is just to bring down the concentration to much lower concentrations, so that there is enough distance between these molecules so that they can behave as themselves. So this was about the concentration quenching, wherein which if you increase the concentration, that increase in the concentration will itself behave as a sort of quenching effect. So we call it as a self-quenching, and that is how the fluorescence intensity is lost because of this concentration quenching. So with that, I'm winding up with this particular session. So I'll just briefly take you through that particular slide where we had all those different types of quenching which we had just now discussed. The first one was static quenching, the second one was dynamic quenching, the third one was chemical, and the last one was concentration quenching. Thank you very much for your patience and time.